point, we have gone through most of the steps in our implementation plan. Now we're going to focus on configuring GRE tunnels. Verification and testing will be done throughout the lesson. We will debrief using a specific lesson, in which we will gather our conclusions and summarize our findings. Our network looks like the topology in the upper left panel. We have a working IPsec VPN tunnel, serving as a backup to our private WAN. We have tested and verified these operations. The new information you're seeing here is related to our GRE tunnels. We will source those tunnels on the loopback interfaces that you see in the diagram. On the 10.251 network for the branch office and the 10.252 network for the headquarters. We are going to base our GRE tunnels on tunnel interfaces, which will be assigned the IP addresses shown here, 10.0.0.1 for the branch and 10.0.0.2 for the headquarters router. Even if you're not responsible for configuring IPsec VPNs, you may need to build dynamic routing around them. Remember, IPsec VPNs are not capable of transporting broadcast or multicast traffic, the backbone of dynamic routing in terms of route advertisements and updates. The VPN tunnel is our backup connection, and we want to move to having it as our main connection. If we want to expand on it and run routing protocols across the tunnel, we will need additional configuration. You can see here the options to route over an IPsec VPN. From the simpler point-to-point GRE tunnels, which we will demonstrate, to the more recent virtual tunnel interfaces, VTIs, to more dynamic options, such as dynamic multipoint virtual private networks, DMVPNs, and group encrypted transport VPNs, GET VPNs. Again, in this module, we will demonstrate the point-to-point GRE tunnel option, but you may find the other options more suitable for your specific environment. Remember, GRE is a tunneling protocol developed by Cisco. It is capable of encapsulating a wide variety of network layer protocol packets inside of IP tunnels. This effectively creates, initially, virtual point-to-point links. It is a very common solution for transporting a routing protocol across IPsec tunnels. We will discuss why in this lesson. It is worth mentioning that GRE tunnels do not provide encryption services. In order to obtain confidentiality, integrity, and other security services, you need to combine GRE with IPsec the way we're going to. GRE is an encapsulation protocol. Simply put, point-to-point GRE tunnels will encapsulate routing protocols in GRE first, and then the GRE packets are encapsulated and encrypted by IPsec. You can see in the top right panel how the routing protocols will be associated with tunnel interfaces, which will use the physical interface of the router to send GRE traffic that will have to match the parameters of our crypto map, and that way be encrypted by IPsec. There are some dependencies we need to build. We need to map the routing protocols to run on top of the tunnel interfaces. We also need to tell the tunnel interfaces to use the physical interface with the crypto map attached to it to reach the other side. In the end, IPsec will be encrypting and tunneling traffic that is initiated from one tunnel interface to another tunnel interface. IPsec will be capable of encrypting and tunneling that type of unicast traffic. Our routing protocols are now going across point-to-point links. That's how we can run them inside of IPsec. The figure depicts how the double tunneling occurs and how packets are assembled by each phase. In our particular scenario, the payload of the GRE packets is, again, EAGRP traffic. That packet will be encapsulated within GRE headers, as you can see in the second packet. Then, the GRE packet will be encapsulated again, using IPsec encapsulation, shown in our final packet at the bottom. Notice one of the drawbacks of this solution, which is the extra overhead you're causing by doing double encapsulation. However, it is one of the ways to deploy routing protocol advertisements across the IPsec VPN. These are the configuration steps which we will follow in our demonstration. We need to first create loopback interfaces, because recommended practices call for the use of loopbacks to source our tunnels for more stability. Second, we need to create tunnel interfaces with GRE encapsulation. We will make sure those tunnels are up and running, then configure our routing protocol, in this case EIGRP, to use the tunnel interface as a routable interface and advertise on it. Finally, because IPsec is the one that tunnels GRE traffic across the public network, we need to change our crypto ACL to match GRE traffic so that it will be encapsulated into IPsec packets. Let's begin. In our top right panel, you can see the syntax of some of the commands we're going to use. We'll start in our branch router, building our tunnel interfaces there. Our first step is to create a loopback. We'll follow our topology diagram to create loopback 101 and give it an IP address of 10.251.1.1. Notice the loopback interfaces come up immediately. This is followed by the configuration of the tunnel interface. We'll call it Tunnel 0. We give it an IP address of 10.0.0.1, according to our topology diagram. We need this because this is the network where EIGRP is going to run. In the case of IPsec, we don't really have a tunnel interface. We have a crypto map, and you cannot run routing protocols there. Our GRE tunnels will need a tunnel source and a tunnel destination. From the routing perspective, this is how the branch router finds the other end of the tunnel, virtually. Again, the recommended practice is to source the tunnel on the loopback interface for stability. The tunnel destination will be the loopback on the other side, 10.252.2.2. We're going to need a similar configuration in our headquarters router. So we go there and configure a similar loopback. This time it will be loopback 102. It is the tunnel destination of the other side on 10.252.2.2. Our tunnel interface is also Tunnel 0. We give it an IP address because this is a routable network for EIGRP purposes, and then configure our tunnel source on the local loopback and the tunnel destination on the remote loopback. There must be reachability toward these loopbacks. The reachability in this case is provided by default routes from these routers into the Internet Service Provider cloud. We can prove that in our branch router. If we display the routing table, we have reachability toward the loopback because of the static route. Remember, this is the backup route that we had for our private WAN. In fact, our tunnels are being established and are coming up because all of the parameters are okay. As you look at the routing table, displayed here, you can see the tunnel interface is showing as a directly connected interface. Again, it will be used for EIGRP routing. Notice in the top right panel, there is one command we did not use, tunnel mode GRE IP. In fact, this is the default encapsulation for tunnel interfaces on Cisco iOS devices. We can verify that by displaying our tunnel interface. You can see that this uses encapsulation tunnel. You can see the tunnel sources and destinations to verify your configuration. You can also see that the protocols in transport are GRE over IP. Our tunnel interfaces are set up, but they will not be used until we tell EIGRP to do so. That's why you see in the top right panel the traditional routing commands for EIGRP. We can go into EIGRP and designate the network of our tunnel interfaces as a routable network to send and receive advertisements. Notice we use an exact mask to avoid enabling the protocol on an unwanted interface. Nothing new here, but we need to enable the neighbor to do the same. Now that our tunnel interface on the headquarters router, if we go there, is up and running, we can go into EIGRP and designate our tunnel interface subnet as an EIGRP subnet. Look at how quickly our neighbor relationship is formed across the tunnel. It's EIGRP1. The neighbor, in this case, is the branch router on 10.0.0.1, which is a subnet of our tunnel. On top of that, it tells you that the neighbor relationship is forming across the tunnel interface. Back at our branch router, we need to complete our last step, which is to have the tunnel encapsulated by IPsec. We can do that by applying the same technique and procedure used in our last lesson. Any traffic we want to go through the IPsec tunnel needs to match the crypto ACLs. If we display our crypto map with a show crypto map command, you can see our crypto ACL is not allowing GRE traffic, which means GRE traffic will not be tunneled and encrypted by IPsec. What we need to do is change this ACL to allow GRE traffic from the tunnel source to the tunnel destination. Let's do that. We enter our access list for the VPN, called VPN ACL. We insert an entry that will permit GRE from the tunnel source to the tunnel destination. Let's finish up by configuring the same on the headquarters router. Notice the neighbor relationship going up and down because we're missing this piece of configuration. If we go into our access list, VPN ACL, we can also permit GRE from this local host to the remote end in terms of tunnel sources and destinations. Look how the adjacency is formed again. And now we can test. Notice that from our headquarters router, if I display the routing table, I'm going to see the LAN of the branch network via the tunnel interface and via EIGRP. It's learned via EIGRP, and here's the tunnel interface shown as the next hop, with the IP address of the tunnel on the other side. Similarly, if I go to the branch and display the routing table and see the LAN of the headquarters network via EIGRP going across the tunnel. If we now display our crypto session, and we see entries for protocol 47, which is GRE, and the encrypted and decrypted packets. That's EIGRP traffic going through and being advertised across the tunnel. This also means that if I now ping from LAN to LAN, for instance 10.2.2.2 sourced at 10.1.1.1, I have reachability and I'm going through the tunnel. Here's the trace to prove it. One hop through the tunnel into our headquarters network. We have reached the end of our topic. We can now successfully run EIGRP across our VPN tunnel using GRE encapsulation. We can now move on to our debrief lesson and verify our findings.